Biostat 6611, skills for the rest of your life, bootstraps and probability, it's the bread and butter, baby, what's your jam?
Welcome Bios 6611 to our next lecture on the normal distribution. This, much like the central limit theorem we will be talking about, is the foundation of bread and butter and even the jam. We're going to introduce some properties, discuss the standard normal distribution, also discuss some terminology relating to population moments and how we can describe different distributions, and just a helpful the more you know PSA for your own information. So first, some properties. And let's start off by assuring you you've made it this far, and now everything is going to be fine. You're in the good place. A place where normality rules and reigns supreme, and the properties we discuss will be extremely beneficial and exciting for many of the topics we'll discuss in the rest of the semester. The normal distribution. The first thing to get out of the way is that you may also see it called the Gaussian or Gaussian distribution, and it is one of the most important distributions in all of statistics. The normal distribution has some unique properties that make it extraordinary. First off, the central limit theorem, which we'll talk about in another lecture set. Also, that a linear combination of normally distributed random variables is still themselves normally distributed. This isn't necessarily the case for all random variable distributions. And also, it isn't terrible to work with mathematically. It could be easier, but also there's a lot of things we can do that we can find closed form solutions for with the normal distribution. So let's first introduce the PDF for the normal distribution. It's defined by two different parameters, mu and sigma squared, where mu is the mean and represents the location, and sigma squared is the variance, and that represents our squared scale, or if we just had sigma in the standard deviation, the scale of the distribution. Where of course we can note that because it is the variance, it must be a positive value, so it has to be greater than 0. The PDF for the normal distribution we see here is f of x equals 1 over sigma times the square root of 2 pi, then exponentiate or e to the negative 1 over 2 sigma squared times x minus mu squared, where the sample space for x in this case can be any value from negative infinity to positive infinity. From the PDF, we could also prove that the expected value is in fact equal to mu and the variance of x is equal to sigma squared, but given that there's two parameters, it can get a little tricky to deal with, and so we'll just, for our sake in 611, rely on this as a fact of the distribution to take advantage of. So let's introduce some properties of the normal distribution. The first thing is that the normal distribution is symmetric about mu. So we see here that if it's mu plus x and we take mu minus x, they'll be equal to each other on the PDF. So for example, we see on the screen here that we have a normal distribution plotted out, and we have it in general terms instead of specific values. We have it centered at the value mu here, and then we just have it in terms of the standard deviation for +1, +2, +3 standard deviations. We can again notice the symmetry of the distribution. It has a bell-curved shape, and again, if we were to sort of roughly take any point where we might say we have some value x and we're adding or subtracting it, it will be at the same point on the y-axis for the density. This property also gives us some nice quick rules of thumb we can use for probability, where we know that within the window of that +1 or to -1 standard deviation of the mean, approximately 68% of the data will fall within that window. If we extend out to ±2 standard deviations, we actually see that within this window, almost 95%, actually a little over 95% falls within this range. This tells you if someone were to give you a statistic and say, oh, it's normally distributed, or at least approximately so, and it's 1.5 standard deviations away, well, we now know that it's going to be something that is within that 95% of all data we might expect to observe. And as we get into more extreme windows, we see that getting to 3 standard deviations away, the edge of our figure contains 99.7% of all data, or nearly all of our observed data should fall within this range. This is useful to note because, again, if someone told you, oh, it's 10 standard deviations away, well, that would be an immediate red flag, even if we knew nothing else, that's a pretty extreme value and it's pretty unexpected relative to the rest of the sample we might have or have expected to see. There's also some connections here if you learn more about statistical quality control with Lean Six Sigma methodology, which tries to keep the chance of observing errors at extremely low probabilities at, unsurprisingly, things like 6 sigma away. Another set of properties we can note is that the symmetry of the normal distribution also means that all 3 common summaries of central tendency, the mean, median, and mode, are all equal to mu. So you don't have to have convoluted formulas to figure out what the mean, median, and mode may be for a given distribution based on its parameters. They're all just equal to mu. And just as a quick review, I've put on the slide the definitions to give you a quick refresher. One other piece to note is that with these 2 parameters, mu and sigma squared, if we fix mu at one point here, 0, we can see that what happens to our PDF as we increase the variance from 1 up to 9. And what we see here is that it gets much less concentrated around 0 and it starts to spread out in its distribution. So if we have a purplish colored x is distributed at normal 0, 9, we have much wider tails and spread out over the window of possible values. So just hypothetically, if we were to say, well, what if we observe something around -4? If it was the normal distribution with a mean 0 and a variance of 1, we would say that looks pretty different. Also, we can note there that it's at the edge of the tail of the blue. For the red normal 0, 4, it's a bit different, but it still might be in a not outrageous range, but for N09 we see that it falls decidedly within sort of the middle area of our figure. And so this leads us to an important distribution or special parameterization called the standard normal distribution that we'll be taking advantage of in a lot of calculations. Even if we don't explicitly talk about them this semester, there might be underlying sort of the hood of the statistical machinery. So the simplest form of the normal distribution is when the mean is centered or set equal to 0 and the variance is equal to 1. In this case, we would say x is distributed as a normal 0, 1 random variable, which is specially called the standard normal distribution. The PDF for this distribution we see here is a little cleaner than we saw before because the mu's are set to 0, so they're gone. And then also the variances are 1, so those also nicely sort of fall out. So we just have our observed x squared. Here we can also note, based on the properties of the normal distribution, that the expected value of x is equal to mu, which is 0, and the variance and standard deviation in this case are equivalent since the square root of 1 is also 1. Now let's talk about how we can standardize any normal random variable. So we can transform any normally distributed random variable, so for example x is a normal distribution with some mean mu and some variance sigma squared, into a standard normal variable, which we oftentimes will call for shorthand z as our random variable, being a normal 0, 1. The relationship here for these random variables is fairly straightforward. We'll take our random variable x, we'll then subtract the mean from it, we'll then divide by the standard deviation sigma, and that will transform into our normal 0, 1 standard normal random variable. Nowadays, it isn't always as necessary because we have a lot of computational flexibility to work with the distribution as we observe it, but there are a lot of nice things we can do with the standard normal representation. And because it's so useful, we actually have some special notation as well for the PDF and the CDF. Now, unfortunately, the tech-generated graphics here are not as distinct as I might like, but we can note that lowercase phi of z is our standard normal PDF. And then if we have a capital Phi of z, that's our standard normal CDF. And we'll see that actually put into play a lot when we're trying to calculate potentially p-values, because we might say, what is phi at some given value of z? And so ways we would have to calculate that CDF of yesteryear usually involve hosts and hosts of tables. So for example, I took this from one of the many sources out there, and we can see that they tell us that we can look up, based on a z value, we can look up to the 10th place on the sort of left-hand side column, go out to the 100th digit place in the top, and we can then calculate from the table, without doing any math ourselves, what that probability of the shaded teal area in the figure would be. So for example, if we want to look at what's the probability that z is less than or equal to just negative 2.50, we would go to the table, look here at the negative 2.5, just go to that first column where the 0.00 is, and we'd be able to quickly take away that it's 0.0062. Again, nowadays we actually have a little more flexibility. For example, we don't really have to only rely on tables to get things done. In R, we can calculate the PDF, or the lowercase phi of z, with d norm as the function, the CDF equivalently for capital phi of z as p norm, or if we want to calculate a quantile, or the value z, how that what the value, of z is for a given area under that curve of the PDF, we can use q norm. So for example, we just see on the slide here, if we want to look up the value of negative 2.58, we could then see that the value R returns to us is 0.0143. So that would be the, if we sort of just maybe over here sketch out a nice little standard normal distribution. If we put negative 2.58 here, that value is corresponding to the height of the PDF at that value of z for our standard normal. Let's see if I can write this nicely for us. So normal 0, 1 distribution. Conversely, we could just say we want the CDF, or the area under the curve to the left, less than or equal to negative 2.58. So we could use p norm. We see here that it says that there is 0.00494 yada yada space under the curve here, which I'm shading in now, to the left of negative 2.58. Again, that means there is a lot of information above negative 2.58, but it does give us a quick way to calculate that value. And likewise, if someone said, oh, what would the value of z be if, for some reason, I want to know what it is for a probability of less than or equal to 0.004940016, then we could use q norm to plug that in, and we see we get right back to what our z value was above. And so that would tell us, if we knew for some reason we want to see what area under the curve corresponded on our x-axis here representing the z distributed standard normal variable, we could see what that value would be for use in maybe a formula or a calculation. So we can see here another representation I borrowed from Wikipedia of the standard normal PDF, and we can see some more specific quantities that may be of interest. For example, instead of plus or minus 2 standard deviations being approximately 95%, we can see it's more precisely this negative 1.96 up to 1.96 standard deviations. We can also see here that we have our, assuming the mean is 0, we have at the sort of first layer, we'll say, of the x-axis, the normal distribution as we observe it. The next layer here of the cumulative percent is our CDF, that we're actually seeing that, for example, if we went up to minus 1 standard deviation, to the left of that point is 15.9% of the curve. Likewise, right below that is the corresponding z-score we have if we transform whatever our distribution is onto this unitless n01 space. And then below that even we have the idea of t-scores, which allows some more flexibility and you may see or encounter in standardized testing or scales. So let's briefly shift gears just to introduce the idea of population moments and describing distributions more generally, because it turns out a lot of them are in reference to the idealization of the normal distribution. So far, we've discussed both location and variability of distributions, and really most specifically the normal distribution in this lecture set. But we can also describe two other measures known as skewness and kurtosis of our population, or also a sample. So for example, we have these terms which we call population moments, and they can be what we say about different things. So we see here that what we know as our sample mean, E of x equals mu, is a population moment about 0. And likewise, the E of x squared that we calculate for the computational form of the variance also can be thought of as a population moment about 0. We can also calculate the population moment about the mean, and these are known as the central moment of a distribution. Of the most interest would be the fact that our variance is that population moment about mu, raised to that second power we saw in previous slides. Also, we can note that when we're looking at the central moment of that first order with respect to mu and x, it's just equal to 0 because for the normal distribution, it's perfectly symmetric. Adding to the terminology we love to just throw out there, we also, from these central moments, can calculate standardized moments just by dividing that central moment by the kth standard deviation. So for example, we'll see that skewness is our third moment, and kurtosis is represented by our fourth moment. And for each of these, we have this theoretical way we could calculate the value. Now, for our purposes, it's just going to be more interesting and of use to note what these terms mean. So skewness. This describes the symmetry of the distribution. So the third central moment of the data, like the first central moment, will balance out from the left to the right if the data are symmetric. In other words, if we had something that was, let's say, normally distributed, we would expect skewness to be 0, or in other words, balanced. If we had positive skewness, like in the graph at the top right, we would say it's skewed to the right, and therefore it's not perfectly balanced. And this is the more common type of skewness we see. It is possible, though, to have negative skew or left skewed data, where we see the skewness will be less than 0. In other words, the higher values will be more common and lower values will be more rarely observed. Kurtosis is another way we can describe a distribution, and it gets at the tailedness of the probability distribution. And oftentimes we're really interested in what we call the excess kurtosis, which is kurtosis of some random variable x minus 3. And that's because the normal distribution has a kurtosis of 3. If the excess kurtosis is 0, we have tails that are just like a normal distribution, and we might call it mesokurtic. This is, again, like the normal distribution, but also a binomial distribution when p is equal to 1/2 plus or minus the square root of 1 over 12. We can have excess kurtosis that is positive or negative. If it's positive, we see it's leptokurtic, like our top right figure, and the tails will be heavier or fatter than a normal distribution. This could be a student's t, exponential, or Poisson distribution. If the kurtosis is less than 0, it's platykurtic, and it's lighter or thinner tails than a normal distribution, and we might see this with a uniform or Bernoulli distribution. So that was just a review of some terminology to keep in mind, and you'll also notice people generally talking especially about skewness of the data when they do some exploratory data. And now I just want to leave you with one PSA, a more you know announcement. Again, in statistics, we like to name things multiple names for the same concept and idea, and we also like to reparameterize our distributions. So while we introduced the normal PDF earlier, some people prefer specifying the scale of the normal distribution in terms of the what we call precision instead of its variance. Now there is this nice direct relationship where the precision is just the reciprocal of the variance, so we usually say tau is that term is equal to 1 over sigma squared. The PDF then looks pretty similar to before, where we just substitute tau for 1 over sigma squared. And I just want to introduce it because one of the more common places you'll see this is with Bayesian statistics and derivations, as well as some engineering contexts. And so if you happen to stumble upon it, it is the same distribution. They're just looking at it in a different way that can help with some mathematical calculations and properties. some of which we may have time to explore a little more later in the semester.